Okay, so it's noon, and I guess we'll get started. I'm Stephen Balk at Beth Israel Deaconess Medical Center, DFHCC, and it's my privilege to introduce James Gully to give this Connect Science presentation. I should say before I do the introduction, just so I don't forget, I was told to remind people that the Connect Science series, they've all been recorded, and you can go to the Connect Science website to see what the talks have been, and then you can go back at your leisure to look at some of the previous talks. Also, if you have questions, instead of using the chat, if you could use the Q&A button at the bottom, and then at the end of the presentation, I'll go through the questions and put them to James. And if we run out of time, we'll email the questions to Dr. Gully, and then he will respond. So with that, it's my pleasure to introduce Dr. James Gully. In way of background, he did his MD and PhD at Loma Linda Medical School, did his residency training at Emory, and then went for his fellowship at NCI and stayed at NCI and has kind of gone up through the ranks at NCI, and for the past several years has been the chief of the genitourinary malignancies branch in the Center for Cancer Research at NCI and the director for medical oncology services at the Center for Cancer Research at the NCI. His particular focus, as you'll hear, has been on immunotherapy, particularly for immune poor tumors, including prostate cancer in particular, which is what he'll be talking about now, but other tumors also that are not on their own eliciting robust immune responses. He's been a particular leader in the development of vaccines, including vaccines for prostate cancer, and combining that with checkpoint therapy and other related approaches, and most recently extending to targeting TGF-beta, et cetera. And I would just say on a personal note, I think that he's always been kind of my go-to person for a kind of an unvarnished view of where we are with immunotherapy and where we should be going with immunotherapy. So with that, I'm pleased to introduce Dr. Gully, and the screen is yours.
Thank you so much, Steve, and delighted to be here to share some of what we've learned at the NCI, and we're continuing to learn. This is an ongoing story. It is not a completed saga, but I do think that we have started to come up with a framework in which we can address these T-cell poor tumors like prostate cancer, and we're starting to see initial evidence of activity. And so I just want to share with you the story that we're starting to uncover, and I'd be certainly happy to talk more about this in the question and answer period. So delighted to share a little bit about our quest for an effective immunotherapy for prostate cancer. Now, with prostate cancer, you have this, and with all tumors actually, you have an interaction with the host and the tumor. And this interaction was well described by Ira Mellman and Daniel Chen in their paper in Immunity about 7 years ago, talking about the cancer immunity cycle. And I've taken and modified that a little bit, talking about the cancer immunity cyclical evolution, because I do believe that this is an ongoing process. Basically what happens is you have a tumor cell, and that tumor cell often has multiple mutations and other target antigens. And what can happen here is you can get these antigens that become in dead and dying cells can be taken up by antigen presenting cells like the dendritic cell shown here and presented in the lymph node to T cells, and these T cells can become activated and can travel throughout the body, can go into where the tumor microenvironment is, can come out of the blood vessel, can recognize the tumor, and then potentially can kill the tumor. Now, this is a process that can become better over time, so that in those immune cells that can recognize and kill the tumor, that tumor cell is killed in an immunogenic manner, and that can lead to additional antigens that become presented to the immune system. And this can be an ongoing iterative. Now, if you turn that on its side and you follow this over time, you might start out with an immune response against PSA, let's just say, for sake of argument here. And then potentially over time, you could expand an immune response so that it's not just against PSA, but it may be against other well-described tumor-associated antigens or mutation antigens. And perhaps by the time you end up, most of your immune response is going to be against those tumor-mutated antigens. And so this ongoing evolution is kind of the 8th E in the process. So with prostate cancer, what you have is a cancer that has very little immune activity, and you don't have a high tumor mutation burden. That may be part of the issue. Perhaps there's not as much expression as HLA, or the antigen processing machinery may be damaged in some cases. But for whatever the reason, there's very little immune infiltrate within most prostate cancer. So perhaps one way to address this is by engaging the immune system by the use of a vaccine. And if you can get a vaccine, you can prime the immune system to recognize a tumor-associated antigen, and those T cells could then become expanded. They could go throughout the body and eventually to the tumor, and potentially could recognize and kill tumor. So in order to study this, about 15 years ago, we embarked on a series of clinical studies with PROSTVAC, or PSA Tricom. This is a vaccine that is made in these poxviral vectors. The initial vaccination is given with vaccinia, a large poxviral vector that is quite immunogenic. But then the subsequent vaccinations are given with fowlpox, another poxviral vector that allows for continued boosting of the immune response. Within these poxviral vectors were encoded the entire gene for PSA, as well as 3 different human co-stimulatory molecules. The thing about these vaccines is they can be grown up in large quantities, frozen down, and simply taken out of the freezer and injected into patients. So our initial first-in-human study, published about 13 years ago, showed that this was safe to give in patients with advanced cancer. We did a subsequent follow-up phase 2 study showing that there was great immune responses, and that there was a suggestion of a correlation of immune responses and survival. And a subsequent larger clinical endpoint study showed that while there was no improvement in progression-free survival, the primary endpoint of the study, there was a suggestion of benefit in overall survival, which was a secondary endpoint in the study. In order to follow up on this finding, we did a randomized phase 3 study in which patients were randomized to receive vaccine alone, vaccine with GM-CSF, another immune stimulant, and empty vector placebo. And in that study, what we found was that there was no difference in overall survival. Now, I would point out the previous study, this was done in the era where only docetaxel was approved, and this subsequent study that we published last year was done in a later era where there were multiple therapies approved. The question we came up with, that everybody came up with, was what is going on here? Why did we not see a signal here? Is it because there is no biologic activity of the vaccine, or is it because there's insufficient biologic activity to lead to a clinical response? So in order to look at that in the context of tumor immunity cycle, we looked at, could we engage and expand that immune response? And if so, how much are we seeing? And was there any evidence of evolution of that immune response? Well, this is data from multiple clinical trials that we published about 6 years ago, suggesting that with PSA TRICOM, what we see is about half of the patients, a little more than half of the patients, can mount an immune response to PSA, the target in the vaccine. And in those patients that mount an immune response, the median fold increase in PSA-specific immune cells was 5-fold. The absolute number of those PSA-specific T cells is very similar to the flu-specific immune T cells in those same patients. So we believe that that's a relevant number of immune cells, but perhaps not enough for cancer versus flu. In addition, the evolution of the immune response, you can see here that of those patients tested, and we only tested 28, but 2/3 of them had evidence of this antigen spreading. That is, immune responses to targets found in the tumor, not found in the vaccine. So indirect evidence of immune-mediated killing going on. However, the real question is, okay, you can measure those immune responses in the periphery. What happens in the tumor? Are you driving a sufficient number of immune cells to the tumor, or are you driving any immune cells to the tumor? So we looked at this in a paper published earlier this in patients who are in the neoadjuvant setting. So patients who got a biopsy at baseline, they got a series of vaccinations, and then at 2 months, basically got their radical prostatectomy. And what we found in those patients, what we compared as a primary, the immune infiltrate at baseline versus the immune infiltrate at the end of the vaccination period, and 30 days after the last, a week after the last vaccination. And what you can see here is that this is a multiplexed, multispectral imaging picture, and what you can see in yellow and in green are the CD4 and CD8 cells. And this is in the pre-biopsy, and this is very typical for the pre-biopsy specimens where you see very few immune cells. This is an exceptional responder. You can see the immune infiltrate here, basically a tertiary lymphoid structure with near the tumor, next to the tumor, adjacent to the tumor, and with multiple CD4 and CD8 cells. This was not what we saw with everybody. I do want to point that out, though. However, what we saw overall was that those patients who mounted an increase of at least 2-fold or greater in their CD4 infiltrate, that was 17 out of 24 patients. And for the CD8 infiltrate, an increase of at least 2-fold was 14 out of 24 patients. Now, this was in any of the tissue compartments. I want to break this down a little bit further for you in a supplemental table that we, that we had in the paper, because I think this is important also. And this is, you can see CD4 at the top and CD8 at the bottom. The log fold increase in the tumor is up, so you want this, this is not like the bars we're used to seeing in clinical research. You actually want the waterfall to go up in this case. What you're seeing is that you do see about a little over half of the patients having a good increase here intratumorally in CD4, maybe even a little bit more at the invasive margin, and even more in the normal tissue. And you can see this is a log fold, so this is a natural log, so this is a much greater increase in immune cells. And then in T cells, you can see the same type of thing where you do see increase in intratumoral, increase in invasive margin, but perhaps even more you're seeing in the normal tissue and invasive margin than intratumoral for these. So perhaps what we're seeing is we're able to push the immune cells to the tumor microenvironment, but there's still maybe an issue getting it into the tumor itself. This is very much aligned with what Larry Fong showed with Sapulacel T Provenge, where following infusion prior to prostatectomy, they saw an increase in immune cell infiltrate, but at the tumor normal interface. So what goes on in those cells that make it into the tumor? Well, if you have a T cell that can recognize the tumor, what happens is it starts to kill that tumor. And one of the things that it does, it makes immune mediators such as type 1 cytokines. These include things like gamma interferon. Well, gamma interferon has long been shown to be able to upregulate PD-L1 on the tumor cell. So what happens with that is that causes the binding by the T cell to this PD-1 on the T cell, and that shuts down a T cell. So you kind of have a stalemate here where you have a T cell that is capable of recognizing and killing the tumor, but not able to do so because of the stop signal sent by the PD-L1 interaction with the PD-1. Come in with an antibody to either PD-1 or PD-L1, you can allow that T cell to become reinvigorated to go ahead and kill the tumor cell. And in fact, data that was published about 8 years ago by Janice Taub from Hopkins, beautiful data showing the exact same areas where you see this immune infiltrate here, these are CD8 cells, is the exact same areas where you see the PD-L1 expression, and this is the older nomenclature of B7H1. So where are we now with prostate cancer and these PD-1 or PD-L1 inhibitors? Well, this was beautiful data published last year from Memorial showing that basically they took 1,000 patients and they found that they had prostate cancer, and they sequenced them, and they found that 32 were MSI high, had lots of mutations, so very low numbers, 3.1% overall. If you break that down into castration-resistant prostate cancer or not, about half of, 2.5% had the MSI high rate was about 2.5% in non-castrated prostate cancer, a lot of these localized, and about 5% for patients who had castration-resistant disease. Now, of these 32 patients, 11 of them were treated with pembrolizumab. And what you can see from these treatment is that out of these 11 patients, 6 of them had decreases in PSA of at least 50%. And of those 6, 5 of them had disease that was measurable by RECIST, and 4 of the 5 had partial responses. So a very interesting signal suggesting about half of the patients that are MSI high can respond to immune checkpoint inhibitor as a monotherapy. So this brings up this algorithm that if you have a positive biomarker, which right now, based on FDA approvals, is MSI high or tumor mutation burden high, which is for the MSI high, again, as we talked about 5% of patients with metastatic castration-resistant prostate cancer, you probably have a chance of responding to pembrolizumab, and the response rate based on several case series is around 50%. However, if you are in the majority of patients that are biomarker negative, you're not going to respond to PD-1 or PD-L1 inhibitors, and this has been shown to be the case in multiple studies, although there may be other biomarkers out there, and I'm not saying that these are the only biomarkers that will be working, but right now, the majority of patients do not respond to immune checkpoint inhibitors. The question is, can you take a tumor that is a cold tumor like prostate cancer and turn it into a hot tumor by the use of a vaccine and get possible activity with that combination of vaccine and checkpoint inhibitor? In order to address this, we looked at a group of patients, and this was a two-part study, I should just mention up front. So what we wanted to get to is this neoadjuvant cohort where we could look at the tumor microenvironment and understand what the immune infiltrate was at baseline and what it was following treatment. But in order to take this combination approach into the neoadjuvant setting, we needed to prove safety in a lead-in cohort in metastatic castration-resistant prostate cancer. So we've completed that 12-patient neoadjuvant cohort. Basically, patients had to have no prior chemotherapy, and then patients were treated with PROSTA with immune checkpoint inhibitors. Now, everybody was treated with nivolumab, and in addition, the first two patients were treated with ipilimumab, but because we were going into the curative disease setting, we had a very low threshold for dropping the ipilimumab, and in fact, the first two patients both had grade 3 or greater immune-related adverse events, so we did drop the ipilimumab after that. Here is the spider plot of the PSA responses in those men. What you can see is we had two patients that had really nice long-term responses, and then another patient who had a long-term stable disease on scans, but a slowly rising PSA, much slower than prior to treatment. But the majority of patients did not seem to have impact from this therapy. So I want to just talk about those two patients that had responses. This was actually patient number 1 on the study. And you can see here his PSA went up initially, and then when he started the ipilimumab and nivolumab, you can see it came down very nicely with this triple combination. However, right here he developed hemorrhagic cystitis. We discontinued the ipilimumab and the nivolumab and just continued the vaccine alone. You can see his PSA remained stable for a long period of time, eventually started climbing a little bit. And I want to show you here what happened with his disease radiographically. You can see here's this large retroperitoneal lymph node, 3 centimeters, and then following treatment, you can see went down to 1.8 centimeters, had a partial response, eventually went on to have a complete response. And however, when his PSA started coming up again, we amended the trial to allow reintroduction of the nivolumab, which he hadn't seen since his hemorrhagic cystitis. And when we reinstituted that, he had another decrease in his PSA. His hemorrhagic cystitis never recurred. However, eventually he started having rising PSA, and he developed a inguinal lymph node that was enlarging, and that underwent excisional biopsy, and you can see another drop here. And we're actually looking into that inguinal lymph node, doing genomic analysis to see what we can learn about patterns of resistance in this patient. And this is patient number 4. This is a patient who started out with PROSTA and then eventually got nivolumab, and you can see a very nice decrease in his PSA with a combination, and eventually he had a complete response. Now, I have to mention that this patient subsequently we found out was MSI high, which was, could explain this nice decrease in the response. However, this was an exceptional response. About this point, he developed colitis, and we stopped the nivolumab and just continued on the PROSTA, and his PSA remains undetectable. His MRI and bone scan remain without evidence of disease. It's not common that we see a bone scan go from being positive to being completely normal in prostate cancer. And you can see here, this is 3 years after he started treatment, and he remains on study getting 1 vaccine every 3 months as his only treatment right now. But unfortunately, of those 12 patients, there was only 2 who had good responses, and one of them was MSI high. So not quite the proportion of patients that I was hoping to get with a combination approach. So in order to go back to the drawing board and understand what else we might need to do to address what's going on in the tumor microenvironment, we kind of went back and said, what else is going on in prostate cancer? Well, clearly PD-L1 could be a problem, and that's where much of the field has focused on with the PD-1 and PD-L1 inhibitors. But there are multiple other pathways that can suppress an immune response in the tumor microenvironment, including IDO, TGF-beta, and others. But these were several that we thought we could target. And so we wanted to come up with a study that would put multiple things together to address all of these. And I'm going to share with you a little bit of the rationale behind that, and then go into the study and what we've learned so far. So first of all, to get to the biology of what's going on in prostate cancer after hormonal therapy, and I feel that many of you on the call probably know this even better than me and are involved in these studies. But really, what's going on with these adenocarcinomas is you're getting chemotherapy, hormonal therapy that is going to induce this epithelial to mesenchymal transition, this plasticity, this transdifferentiation, to push the cells, the tumor cells, into more drug-resistant stem cell-like properties. So there are several different drivers of this, some of which we have studied in our group, and we have been able to target from an immune standpoint. So I just want to talk about a couple of them. So first of all, brachyury is a transcription factor that we have developed vaccines to, which we'll talk about. TGF-beta is well known by everyone. We have a bintrafusp alpha, which targets this. We'll talk a little bit about this. And then IL-8 may be also important in this, and we have worked with antibodies and small molecule targeted therapies. I'm not going to be talking about this, however. So first, let's talk a little bit about brachyury. It was identified as a gene that was transcriptionally differentially expressed in tumors versus normal tissue by data mining. It's involved in embryonal EMT, and so the notochord, you turn on the EMT to get the notochord cells to migrate. And what we find is that it's absent in the vast majority of normal tissues, but it is expressed in testes. It's expressed a little bit in thyroid, but one could argue that it may be a cancer testes antigen or similar to a cancer testes antigen because it's expressed in testes as well as a large proportion of cancers. And it appears to be differentially expressed in metastatic cancers versus primary tumors also. So there is a body of evidence in prostate cancer, and I'll get to that in a little bit. So what does brachyury do? Well, it is involved in the induction of EMT, and this metastatic process, as you all know, epithelial cells, they turn more mesenchymal, they lose their tight junctions, they gain properties to allow them to invade and migrate and then metastasize. Interestingly, a lot of times they can revert back to epithelial cells in the metastases, but often there is a remnant of these more mesenchymal cells that are more resistant to therapy. So when you come in with chemotherapy or hormonal therapy, you can kill off the more epithelial cells and leave behind these more resistant cells. So what happens when we look at brachyury in the lab? Well, if you have a brachyury low cell line and you knock in brachyury expression, what you can see is that there's downregulation in epithelial markers, and there's upregulation in these more mesenchymal markers, fibronectin and vimentin. And what that leads to functionally is an increase in the ability to migrate and invade in matrigel plug assays. And if you do the reverse, if you take a brachyury high cell line and you knock down brachyuria expression, what you can see is the reverse thing happening. You can see an upregulation in epithelial markers and a downregulation in mesenchymal markers. And this also is associated with a decrease in migration and a decrease in invasion. So it appears to be quite important in the metastatic process. So I'm going to show you in two murine models the impact of brachyuria expression. And this is a lung micromets model where you give a subcutaneous tumor and then measure the lung metastasis. If you look just at the primary tumor at day 15, you can see very little change in the level of, the volume of tumor, whether or not brachyuria is knocked down or whether it is not knocked down. But when you knock down brachyuria expression in the you can see that the impact on metastasis is profound compared with the expression that's wild type. Now, if you look in the IV model, so you say, okay, well, this is a sub-Q model. Now, what about IV? If you just give the tumors IV, well, you see the same type of thing. If you knock down brachyuria expression, you get much less, many fewer lung metastases that are set up at day 45 in this model. So this brachyuria has been studied in prostate cancer, perhaps best by Dr. Pinto in Portugal. And he's shown that it's associated with prostate cancer progression and aggressiveness. Basically, just pull your attention to this figure, part of the figure here, where you can see in non-neoplastic prostate, very low expression, but in metastatic, in prostate cancer and PIN, intermediate and higher level of a number of cells that are positive in metastatic disease. And this is true for cytoplasmic staining as well as nuclear staining of the brachyuria. He's also shown in a subsequent article that it's a modulator of AR activity and it keeps resistance to therapy. So from an immune standpoint, what we've found is that often in our studies, and these are not studies with brachyuria-based vaccinations, but other vaccinations like PROSTVAC, we would see immune responses to brachyuria that emerged. So this antigen spreading was frequent to this target antigen. And we can readily generate immune cells from either normal volunteers or from cancer patients to brachyuria with in vitro stimulation. And these immune cells, these T cells, could kill brachyuria positive tumor cells in an MHC restricted manner, suggesting that it could be a immunogenic target. So what I'm going to do now is just share with you a couple of bits of information for a clinical trial that we have put together that we refer to as our quick efficacy seeking trial or QUEST trial. So the first one is a vaccine, and as you can imagine, this is a vaccine that targets brachyuria. So we published about 3 years ago our phase 1 study of this poxviral based construct that instead of targeting PSA is now targeting brachyuria. We found that it was well tolerated, no dose limiting toxicities were seen, and 28 out of 34 patients developed brachyuria specific immune responses. So instead of about a little over half, you're now getting a little over 3/4 of the patients that are responding to this vaccine with a good number of immune cells. And perhaps it's because brachyuria is not expressed in normal tissue apart from perhaps the thyroid and the testes is immunologically irrelevant because of the absence of MHC. But perhaps because of that, there's less thymic selection against brachyuria when the T cells are being trained. And so that may be one reason why we're seeing higher proportion of patients able to mount an immune response against it. Okay, I want to also mention though that vaccine may not be enough. Maybe we want to also further expand those immune cells, and cytokines are a great way to expand immune cells. I just want to mention here a cytokine that we've been working with called N803. So this is an IL-15, but it's a super agonist. So there's a 1 amino acid substitution that allows for better activity in the better function of the immune cells, and this affects both NK cells as well as T cells. So what it is this IL-15 that's bound to the IL-15 receptor sushi component, so that this stabilizes this, and then that is also bound to an IgG1 Fc component. So this has a much longer half-life than the protein. So the protein itself has a half-life of about 40 minutes, and the half-life of this complex is about 25 hours, and it's a superagonist. So what happens with NK cells? Well, you get a much higher number of NK cells after giving this, and not just a higher number of total NK cells, but it's the right type of NK cells. So these are high effector, activated, and active terminal effector NK cells. What does that translate to on a killing assay? Well, you can see here that on this killing assay, that if you treat the cells with PBS, you can get a little over 20% of the tumor cells killed. If you treat it with this N803, you can get a little bit over 60% of the cells killed. How does that translate into a tumor treatment model, where you can see in this lung Mets model, much better suppression of lung metastasis with this N803. So how about in combination studies? So this is a combination in the 4T1 murine model with resection of the primary tumor at day 15, combination of N803 and PD-L1. And what you can see is at day 13, the last day of treatment, there's really no difference in the primary tumor growth. But if you look at the lung metastasis at the end at day 27, you can see that there is a substantial decrease with the combination. And here's with N803 alone, here's with PD-L1 alone. How about combining it with vaccine? Well, this is in a CEA transgenic model with a CEA-based vaccine, and then adding it with the N803. You can see with the combination, you get better activity than with either the N803, also known as ALP803, older nomenclature, or vaccine. Finally, I want to talk about two other things, and that is TGF-beta inhibition and PD-L1 inhibition, and then I'm going to talk about IDO inhibition. But bintrafusp alpha is an innovative first-in-class bifunctional fusion protein that blocks PD-L1, which we all know PD-L1 and PD-1 pathway is very important in immunology. But it also sequesters TGF-beta. And this is important because TGF-beta is involved in fibrosis and impaired drug access, epithelial to mesenchymal transition, which is associated with drug resistance. TGF-beta is also involved with tumor angiogenesis. And importantly, it also suppresses the immune response. So by sequestering TGF-beta within the tumor microenvironment, one can remove these negative biologic consequences of TGF-beta, potentially. So we did the first in human dose escalation trial entirely at the NCI. We treated 19 patients. It was well tolerated. We'll talk a little bit about side effects later. It sequestered all of the activated TGF-beta in the plasma throughout the dosing period, and also had a good target occupancy on the PD-L1 side. And there was, in this heavily pretreated patient population, there was promising clinical activity in this phase 1 dose escalation with 1 CR and 2 PRs and another near PR. All of these were sustained. I can say that there's been over 700 patients treated in 10 different tumor types now with bintrafusp alpha. And I'm gonna just share with you 2 bits of data from expansion cohorts within that phase 1 study. This is data that was just published earlier this year in the Journal of Thoracic Oncology, and patients were treated in the second-line setting in lung cancer with either 1,200 milligrams, which is the recommended phase 2 dose, or 500 milligrams to get additional data on the PK and pharmacodynamic activities. What you can see here is that there were nice responses that were definitely durable in both of these groups of patients. And this has actually led to an ongoing randomized study in lung cancer comparing bintrafusp alfa with pembrolizumab in the frontline setting. I also want to share with you an emerging story with bintrafusp alfa and HPV-associated malignancies, because I think this is very interesting. This data comes from a study we did in an expansion cohort, rather, we did in the phase 1 study, as well as an ongoing phase 2 study at the National Cancer Institute. And this data is in press right now in the Journal of Immunotherapy for Cancer. And you can see here a nice prolonged response rate in patients with HPV-associated malignancies of a variety of different types of HPV-associated malignancies. And indeed, when you look at the response rate, overall 31% objective response rate by RECIST, which is very interesting. And if you look at the addition of the delayed responses that we often see with immunotherapy, it brings it up to 36% response rate. TGF-beta is also associated with T-cell exclusion. So this is data that you probably remember being published in Nature 2 years ago. The patients were binned into 3 different bins: immune cell desert, a quarter of the patients; immune cell inflamed, a quarter of the patients; and half of the patients were immune cell excluded. And if you looked at those patients who were immune cell excluded, and you looked at their TGF-beta gene signature score, what you found is that those patients who had a lower TGF-beta immune signature, those patients were more likely to have objective responses than those patients that didn't have that gene signature score. They went on to show in data that if you gave PD-L1, you could get 1 out of 10 mice cured, TGF-beta none, but the combination of the two, you got 7 out of 10 mice having CRs. And in addition, when they looked at the tumors, much greater immune infiltrate than either treated with anti-PD-L1 alone or anti-TGF-beta alone. So I think this combination makes a lot of sense, and having it in one molecule also has advantages. Finally, I'd like to talk a little bit, one slide about IDO inhibition. I realize that IDO inhibition in combination with PD-1 inhibition has not shown activity, but the question is, will it show activity when you combine it with vaccine and cytokine to further boost the number of immune cells? And we don't know that. Why is IDO important? Well, it is an enzyme that catalyzes the conversion of tryptophan to kynurenine. And kynurenine, and it's made predominantly in the tumor microenvironment. And kynurenine, it drives T regulatory cells and causes the effector cells like CD8 cells to undergo apoptosis. So really important to block this enzyme, at least from a theoretical basis. So I'm showing you this picture here of the building 10 at the NIH. This is the building that all the patients get treated in. And I'm showing you this just to remind myself to talk about the exceptional opportunities we have here at the NIH. One of those is a mechanism put in place by Congress in 1980 called the Cooperative Research and Development Agreement, or CRADA. This was put in place to accelerate private-public partnerships and accelerate things that were found at the NIH into the clinic in industry. And so it allows us to work together with industry. One of the nice things that I've pushed for and are in all of my CRADA agreements is the ability to use another agent not found within the CRADA if it is agreeable to all parties. And what that enables us to do then is, without having to go back to the lawyers typically, is just talking with the scientists at the company, can we combine two different and go forward. And so based on that, we've been able to take the vaccine targeting brachyury, as well as this N803 and this TGF-beta inhibition with bintrafusp alpha and the IDO inhibitor. So 4 different agents from 4 different companies targeting 5 different immune pathways, if you will, that we believe may be important in prostate cancer. So I'm going to share with you a little bit complicated trial design for our quick efficacy seeking trial, or QUEST trial. The first part of the study, basically it's an adaptive design trial that is a sequential approach. So the first part of the study, actually that I'm not showing you here, is just a safety arm where we're looking at the combination of the N803, which is the IL-15, with the bintrafusp alpha, the But in the prostate specific part, there's the vaccine with the bintra as the initial cohort. Then if there's safety in this arm, then we will add in the N803, the IL-15, and then if there's safety, we'll add in the epacadostat, the IDO inhibitor. And we'll get 13 patients treated in each of these before we then go to a randomized portion. Now, we only go into those randomized arms if there's at least 2 or more patients who have a response. Response is defined as a sustained PSA decrease of at least 30% or an objective response by RECIST. And so I'm going to share with you the data that we have thus far on these patients. So we've enrolled so far 43 patients. 14 patients were in the initial safety of the N803 and bintrafusp alpha. That was shown to be safe, no issues. We've then enrolled 13 patients in each of these next 2 arms, 2.1 and 2.2, and we've started enrolling in the 2.3, which includes the epacadostat. I'm going to share with you the data from these 2 arms, some of which was presented at ESMO and AACR recently. So this is the overall table of responses. What you can see is 1 out of 13 patients had a sustained PSA response. So not making it for this arm to move forward. And the best response by RECIST was stable disease. In arm 2.2, however, 5 out of 12 patients have had a PSA response that is sustained. And of the 3 patients evaluable by RECIST, 2 of them have had a partial response. I'm going to go into a little bit more detail about both of these. So here's the waterfall plot. You can see arm 2.1, 24 weeks response for this one patient, but the rest of them didn't have a response. And here's what we see with arm 2.2. Now we have 12 patients that have been on at least 12 weeks so that we can take a look at their imaging, and I'll look at their PSA responses. And these are the 5 patients that have had responses. This patient here, you can see we did not count as a response because the maximal PSA decrease occurred after radiation treatment for a lesion. But you can see these responses are quite durable, out to getting close to a year and ongoing right now in some of the patients. So, and here's the spider plots of the PSA. You can see this patient, even though we documented as a 24-week response from the time of response, continues on study with stable disease, and many of these other patients in arm 2.2 also do. This is just showing you one of those patients in arm 2.2, patient 29. You can see inguinal lymph node and a retroperitoneal lymph node, both between 2 to 3 centimeters, and these went down to less than a centimeter on study. And you can see this was the PSA decrease and sustained decrease over a year now since starting study. And the prior treatment on this patient, you can see, had docetaxel for castration-sensitive disease, CYP-T, abiraterone, and enzalutamide. How about side effects? Well, the side effects one sees with this treatment are similar to the side effects one sees with the immune checkpoint inhibitors. With the addition of the N803, the IL-15, there are more flu-like symptoms seen, but overall these are relatively low grade. If you look in the grade 3 treatment-related adverse events, you can see it's similar in terms of proportion of patients having those with each group, between 2.1 and 2.2. And there were no grade 4 or greater treatment-related adverse events. I do want to point out one thing here, though, and this is this isolated ACTH deficiency or isolated adrenal insufficiency. And you can see that 4 patients had this overall. And who are those patients? Well, all of those patients also had responses. So what is the potential for the those responses to be impacting the PSA declines and objective responses seen in these patients? Well, obviously ACTH made by the pituitary acts on all zones of the adrenal cortex, especially on the zona glomerulosa where cortisol is being made, but can act also on the zona reticularis where adrenal androgens are being made. And so these adrenal androgens obviously could impact prostate cancer growth, and that's one of the reasons we target adrenal androgens with abiraterone, for instance. So some remaining questions on this study is how many of the patients in this study were MSI high? Well, we retrospectively went back and identified patients, and we were able to categorize 3 patients as being MSI. A 4th patient did have PMS2 loss, and 1 patient we have pending, so we'll find that out further. How about the adrenal insufficiency? Was there any contribution of this to the responses seen? Well, 3 patients, as I mentioned, did have isolated adrenal insufficiency. However, these 2 patients here with the X's, those patients had the onset of adrenal insufficiency 2 and 6.5 months after the PSA response, so probably not a factor there. And this other one had adrenal insufficiency after several months of PSA decline from peak PSA, but before having a response compared with baseline. So it's uncertain as to whether there was a change in the adrenal androgen. So we are actually measuring this on all of these patients, and hopefully we'll have answers. Additional questions are, will this response rate hold up with a larger number of patients? How durable will these responses be? And what is the contribution of each of these agents in the triplet to the activity seen? And that's going to be the focus of a subsequent trial that we hope to get going in the near future. So overall, what we know from the literature is in unselected patients, about 2 to 2.5% of the patients might respond to immune checkpoint inhibitor therapy with prostate cancer. However, with Quest, perhaps we're getting an increased number, and what that proportion is going to be, it's uncertain yet. This is very early on, very early days. A lot could change this, but I think an interesting signal that bears further follow-up. So what I'd like to share is that basically immunotherapy can be powerful, can lead to very nice responses, but I think it's going to take a combination approach in prostate cancer that really addresses each of the critical elements necessary in the tumor immunity cycle to engender an immune response. And I personally think that approaches that stimulate an immune response, that expand the number and function of those immune cells, and facilitate the functionality in the often very negative tumor microenvironment that is is such a killer environment for immune cells, I think that's going to be critical as we address immune deserts like metastatic castration-resistant prostate cancer. I'd just like to acknowledge the amazing group of people that I work with in the clinical cancer immunotherapy program here at the Center for Cancer Research. And this is the core group that I work with. These are other investigators that are not in the branch, but we have collaborative trials ongoing. And then the translational laboratory team that I work very closely with that do the immune analysis that I talked about and many of the preclinical studies that I talked about. And finally, patients and their families. And I'm going to stop here, and I would be happy to take any questions.
So, Dr. Gully, thank you so much for incredibly enlightening. I think maybe disappointing in the beginning, and then very exciting towards the end. It really looks like there's the potential to elicit these responses. I had a couple quick questions, and then there are a few questions that people have asked on the Q&A.
Sure.
On the latter part, these very substantial responses that you're seeing, have you anything in the peripheral blood, for instance? Do you see any evidence of obviously antigen-specific T-cell responses, or anything along those lines? And any idea what those antigens might be if they are responding?
Great question. So we have looked at antigen-specific immune responses, and we do see brachyury-specific immune responses in these patients. There doesn't, so that seems to be probably a necessary component, but not sufficient. So the generation of peripheral immunity, immune cells that can target tumor appear to be necessary, but I think really what's going on in the tumor microenvironment is going to be more critical. And so we have started to see different subsets of NK cells that may be, that are clearly activated with the IL-15. And when we look between the two arms of patients, the arm that got the IL-15 2.2 and the arm that didn't 2.1, there are differences, substantial differences in NK cell number and activation. It's not clear if that is what is resulting in the responses or not. I think we're just going to need to have further numbers to be able to tell us what we can learn from the peripheral immune response that can help us predict who's going to respond in the, and as well as correlating that with hopefully biopsies. Unfortunately, we started to see these responses about the same time COVID hit, and so we, as an institution, went to not doing any research biopsies, which kind of was really a painful thing for me to see all these responses and not be able to get tissue to be able to understand what's going on.
Oh, that was the question I was going to ask you next about biopsies. So, and I guess more generally then.
We're back open though for biopsies, and so we will be getting those going forward.
Do you think that, I mean, the modest responses to the PSA or the BRCA, kind of single antigen, do you think you need a more diverse, set of antigens? And are there really tumor-specific neoantigens, or is it tissue-specific antigens? Kind of an open-ended question, I guess, but your view on that.
Absolutely, great question. So, to me, it's a little bit. I see the vaccine as serving as the spark to get the fire going, and you're going to need more than just a spark to burn wet wood. You're going to need to follow it up with other things. But if you can get the appropriate tumor microenvironment to get that fire going, if you will, if you can combine it in the right way, I think you can get this antigen spreading. The immune system is incredibly capable of identifying neoepitopes on its own or tissue antigens on its own. And so we've shown that we can generate these neoepitopes with coming in with an off-the-shelf based vaccine, or sorry, we can generate immune responses to these neoepitopes when coming in with an off-the-shelf vaccine. Whether that is enough, or what the right combination of agents needs to be, or whether you need to come in with a neoantigen vaccine because maybe that catches on quicker, or whether you need to come in with adoptive cellular therapy because that can overload the, that can really shift the balance to tons of effector cells. It's not yet clear to me, but if we are seeing a substantial proportion of patients that are responding, if we continue to see that with a combination approach, an off-the-shelf combination approach, then I think that's logistically a lot simpler to do than neoepitope-based approaches where we're still trying to figure out the best ways to identify those neoepitopes. And we have some super smart people that have made big inroads, but I think our immune system is still smarter than we are.
There are a couple questions kind of in the earlier part of the talk about whether there is, in kind of prior to treatment in the biopsies you're looking at, evidence of kind of T cell exclusion. So there's not very much in the way of T cells, but the ones that are there, are they at the periphery? There's this idea that they're just not getting into the tumor, but they are actually there. And related to that, I guess PD-L1 expression in the tumor.
Yeah, absolutely. So those are two critical questions. So it does appear to me that there are issues with the immune cells getting into the tumor. There's certainly some getting in there, but not in every patient. I think there are issues with the design of how we did that study, where we were comparing biopsy beforehand to whole prostatectomy specimen afterwards. But we tried to be very careful in how we controlled for that and everything. I think the big issue though is we probably are seeing immune cells getting to the tumor, but not getting, to the tumor, near the tumor or at the tumor normal interface, but not a ton of cells in. And whether that's a TGF-beta issue, whether there's other cytokines, chemokines that are creating a negative influx potential for the T cells, that we don't have a clear answer on yet. But I think that anything we can do to soften the tumor microenvironment, tumor-targeted cytokines are one of the options that we are looking into. And initial data with an agent called NHS-IL-12 along with vaccine looks really promising. So the NHS-IL-12 is a tumor necrosis targeting antibody that brings with it the payload of IL-12 to really get the IL-12 in the tumor microenvironment. And preclinically, beautiful data with that and actually a neoepitope-based vaccine.
And I guess there's time maybe for one more question. Was in the MSI high patients or with high tumor mutational burden, responses to just vaccine? So with these patients, if you can tickle, I guess the idea is an immune response.
Yeah.
Or if they fail to checkpoint blockade, have you looked at whether they might respond to vaccine therapy?
Great question. So the way that I see this is I don't think patients that have MSI high are going to be likely to respond to vaccine. They already have a lot of mutations. However, obviously something's going wrong in the immune system. The way that they're interrogating those mutations may not be right. What we did notice in our one patient that was MSI high is he had a complete response, which we don't see very often in immunotherapy generally, and certainly not in prostate cancer. Could he have got it just with the nivolumab? Yes, absolutely, potentially. Did the vaccine play any role here? And that's what we don't know. I guess one could speculate that the vaccine generated an immune response that could allow for the more immune cells to go to the tumor and target tumor cells. Certainly, he had an incredible immune response. Perhaps the continued immune response for the last year and a half when he hasn't been getting nivolumab is all because of the incredible response his immune system did in the first year and a half that he was on the nivolumab. Or perhaps the vaccine had some impact. It's impossible to know, and only one patient.
So now I'll squeeze in one last question, and this would be the last one, which just came up. The stage in tumor progression that might be most responsive to immunotherapy. I think the idea is earlier, for instance, versus late. Do we need to move it earlier?
Yeah, so I would agree. I think in the, if you look at the balance between immune system and tumor and the ability to fight, the more systemic therapies a patient has had, or even radiation therapy, and the more the resistant cells are around, they're often resistant not just to those therapies, but resistant to multiple types of killing, including immune-mediated killing. So anything that can drive up, one thing that I didn't mention is that even though brachyuria is associated with a target on immune cells, it is also associated with this epithelial to mesenchymal transition, and these cells are actually more difficult to kill, both by hormonal therapy, radiation therapy, chemotherapy, but also by immune cells. So even if we're coming in with brachyuria targeted T cells, if you get super high levels of expression of brachyuria in the tumor, it's one of the few times where you increase the amount of target on the tumor and you decrease the ability for the T cell to kill the tumor.
Okay, well, I guess we're out of time. So I want to, Dr. Gully, I want to thank you very, very much. I enjoyed your talk as always. And if people have more questions, I'm sure that you'll be willing to respond offline.
Happy to.
Okay, and thank you for
Steve.
everyone listening in.